Okay, so what we're going to do today, and then the last session, which will be the next session, is we're going to do an end-of-term review. And this DVD recording might be useful to a person when, after you get into calculus, to be able to come back and kind of get a quick sense of, related to this textbook anyhow, of the key topics in trig. And then I'm also going to refer you as to which DVD numbers are associated with each section that we've covered. So what we'll do is we'll start out in the first segment here on some of the early fundamentals, the things that most of us struggle with, trying to get our feet on the ground with trig. And then we'll move on into the actual trig functions and equation solving. And I want to point out to you, many of you seem to be pretty weak on actually solving equations. That's probably one of the more important parts of trig, is being able to solve equations. So when we get to that in the review, make sure you try to spend a little extra time, maybe over the holiday and that kind of a thing, on that, which I'm sure you will, right? Okay. Okay. And then we'll just continue on with the review as we go. Okay, so I want to try to be kind of quick today on this. I'm not going to be able to go back and reteach the stuff, but we have that backup DVDs and recordings that you can go look at, and your textbook, of course. So the very first section we covered, here I've cited the section numbers of and the page on our textbook where they're found, and I've also noted what videotape or DVD number is associated with these different parts of the course. So first of all, we're going to do a little quick review of degree and radian measure, because we have to have had our feet on the ground before we can move on into the other topics in trig about degree and radian measure. So let's go ahead and jump at that. Some of this should be just like automatic, almost in your sleep kind of stuff for you. And then it'll start to get a little more exciting further down here we get. Okay. So we all know 0 to 360 degrees. If we're in degree measure, we always put the little degree symbol, because if that symbol's not there, then it's going to be interpreted as what kind of angle measure? Radian measure, okay. And we oftentimes are sweeping, and this doesn't have to be restricted to 0 to 360, but that shows up a little later when we start talking about the unit circle as being 0 to 360 typically, but the angles are not restricted to that. This corresponds to 0 radians, sweeping to 2 pi radians in measure. And related to a circle, which will be, we spent a lot of time using that as a mental kind of image, is 0 degrees here. We measure our angles. Remember, positive angles are measured counterclockwise from the x-axis, the way a lot of our relationships are developed. And then as you sweep on around, you go all the way around, you get to 360 degrees for the terminal side, and you can keep on going. That is equivalent to 2 pi radians, and so that means halfway around here at 180 degrees on the arc is where pi radians would be located. One thing we did, what you want to make sure you don't forget, even though we didn't spend much time on it, is being able to take an angle, might come at you in radian measure, and being able to convert that into degree, minutes, and seconds format for things like astronomy and surveying and that type of application. So let's take an example. Let's say we want to find out degrees, minutes, and seconds for a given angle, and let's say we pick, oh, how about 4.3 radians. 4.3 radians. So we want to develop the degree, minutes, and seconds measure of 4.3 radians. Now we also want to always have a sense of where this is going to be. So if you want to use the circle or the arc here, you can think about rolling this to 4.3 radians. Well, 2 pi is about 6.28. 3 pi over 2 down here, think about that value. 3 times pi is a little bigger than 9. So this value right in here is a little bigger than 4.5, isn't it, in value? And so you can also think of that as, I think a little more accurately, probably around 4.7 radians. So 4.3 radians is going to be hanging right back over in here somewhere, isn't it? As an angle. 4.3 radians there. Okay. So you don't even need that thinking to do this problem. First of all, we got to kick it back to degrees. So rather than asking you folks, I'm today, in the interest of efficiency, I'm just going to talk and write, okay? So we know then that 180 degrees is equivalent to pi radians. So we can see now that we are now in degree measure. And so somebody on your calculator, please punch that for me. 4.3 times 180 over pi.
246.
What? No. Say it again. What did you just say?
Said 246.
Oh, I'm sorry. I thought you said 2.6. Okay. 246.
0.37.
246 point.
So 37185.
37185.
Yeah.
How many decimal places do I want to get this accuracy to be able to capture the seconds of angle? 4. I want to get at least 4 decimal places in my reading I write down. So you said 246.3718.
85
5 what?
degrees.
Was it right at? What's after the 5?
19.
Okay. So I'm going to go ahead and pop that up to from 18 to 9. Okay. And you can punch this on your calculator as well. So that's degree measure. Now, what we do to kick this into DMS is we're going to take the 246 degrees, we're going to be adding to it that decimal portion of degrees, and then we have to remember that in a degree, in 1 degree, there are 60 minutes. So now, take just that decimal portion and multiply it at 0.3719 times 60. 22.314. Okay. Degrees, right? Or no, minutes. Minutes, right? That's minutes. So then we're going to take the 246 degrees plus 22 minutes, and we're going to take the decimal portion of that.
It's 18.84.
Okay, good. And so in 1 minute of angle, there are 60 seconds. And then you're going to, and what'd you say, Deanna?
18.8.
18.8, we'll round that, like you said, to 19. And typically then you just write this down as 246 degrees, 22 minutes, 19 seconds for your approximate answer for 4.3 radians. Okay, just wanted to make sure I went through that with you. That's pretty basic. All right, on to the next item in this section, circular motion. So if we take an object that is moving in circular motion, and I'll just use the standard, we learned early in the course that if we would take this radius and bend it on the arc, that's our arc length, and if we bent that radius and bent it on the arc there so that that arc length was equal to the radius, then the rotation that has occurred here is defined as 1 radian. That's a little less than 60 degrees. That is a little less than 60 degrees. 1 radian. Okay, now back to the arc length stuff. If we take, actually, let me not do that. Let's do this. We have some radius, we have some central angle. This is the arc length, and we learned early in the course that the arc length was equal to the radius times theta. And theta has to be in what type of measure? It's got to be in radian measure. So if necessary, if that's given to you in degrees originally, like say 40 degrees or something like that, you have to convert that 40 degrees to radian measure, multiplying by pi over 180. to be able to find the arc length. Now, if you just take that expression and divide by time, holding the radius constant, that means the object then will be moving on a circular path if you hold the radius here as a constant. Then you see that there's an angular speed here, angular speed, and this over here is distance over time, which is linear speed. This over here is not real good English. Right? Okay, and so oftentimes we'll write this as V equals R omega, R omega. So this is how you can find out how fast something is moving on the edge of a circular arc, or a circular path. And this is how fast the rotation is occurring. The units you oftentimes see here might be in revolutions per minute. Revolutions per minute. And if that's the case, you have to kick that into radian measure, and you know you'd be multiplying the revolution per minute reading times 2 pi radians, equivalent to 1 revolution. And then that gets rid of the revolution units. That turns it into radians per minute, which then allow you to do your calculation properly. Okay. I'm not going to do a, well, maybe I will do a problem. Let's see if I wrote something down here. Nope. Go back and look at the old DVDs or recordings if necessary on that material. Okay. 16 angles also in this section, and this is getting us ready for the development of the unit circle. And so you should not be writing this thing down every time you take a test or a quiz, which I've seen some of you do. This thing should be in your brain.
Not everybody thinks like that.
What?
Like I'm visual, you know?
Oh, okay. Well, if I said, now we all know our 16 angles, don't we?
Right.
Okay, so let's say we're down here. I'm going to be thinking in my brain, instead of actually putting it down on paper, I'm going to be thinking cutting like a cake up into 8 pieces there. And then I know this is pi, and so then this would be half a pi, and that means this is half of that, so that's pi over 4. So you're talking about fractional parts of this. So if I'm talking about an angle here, that's going to be 4 or 5 of those parts. 5 pi over 4. So if I'm dealing with an angle that's 5 pi over 4, what I would draw is I would draw this. And I'd label that 5 pi over 4 without having to recreate the entire image every time I'm doing a problem. So just try to get to that point, and you will get there with a little bit of extra practice as you move into calculus. We also talked about pi over 6. And these were equivalent to, remember, 30 degrees and 45 degrees. Feel good? And multiples thereof as you work your way around the circle. So this would be 1 pi over 6, 2 pi over 6, which is pi over 3, which is equivalent to 60 degrees. 3 pi over 6 is here. 4 pi over 6 reduces to that, which is equivalent to 120 degrees. And without me going through the whole thing, you should be okay with that, I believe. And we can work our way on around. Notice how close I'm putting these points compared to those 45-degree ones. They're close there. They're only 15 degrees off. Right? Everybody okay? 15 degrees off of that? Right. So down here then, this would be 6 pi over 6. I've talked about this before. This would be then 7 pi over 6, equivalent to 30 degrees added to 180, or 210. Now correct me, my mouth and brain and what I write sometimes don't correlate. Okay, so if I start saying something wrong, even though I'm writing it correctly, please correct me. Everybody all right? This one would be 180 degrees here plus 45 which would then be 225. And then we could keep on going, and I don't think I want to take all the rest of the time to do that. Yeah, right? Okay. It's the fundamentals. These are the fundamentals, and make sure you go back to DVD number 1, or recording number 1, and recording probably number 3. What happened in recording 2 is I think we moved over into chapter 8 briefly, which was a right triangle trig. All right? Okay. Let's look at the 6 trig ratios in the unit circle in section 6.2 then. All right, 6.2, the unit circle stuff. All right. Any confusion so far? Tom, is that all right?
Yes.
Okay. The 6 trig ratios in the unit circle. Let me start by taking the unit circle. If we draw our unit circle, which we're very familiar with, radius of 1, our angle measure, remember, is coming off the x-axis here. And there's something I did not say previously this term. Textbooks discuss it, but I can point it out to you now, and I think it'll be comfortable for you. If you go back to what we talked about on arc length, if I took a circle of radius r, and I come up here with some arc length, and I'm going to call it, s, like normal, and here's our central angle, theta, and here's our radius. We know that that arc length over there is equal to r times theta. Now, if we force r to equal 1, bringing it into a scaling like you see here, if we do that, then the arc length measure is this angle measure in value. In value. The arc length will be equal to the angle measure in value. So that means the way the textbook does it is they talk about this being equal to t. Think of that as an arc length. And that's the radian measure. That's radian measure. And if the central angle here was in degrees, that arc length over there is the radian measure, equivalent to this measure in degrees. If you go halfway around, this arc length would be pi. This arc length over here would be pi on a unit circle. Think about that. You know that well, let's say you go all the way around. If you go all the way around, you know that circumference is 2 pi r, and if r is 1, that circumference would be 2 pi. So that's handy. Try to keep that in your head. If you're on a unit circle, which we are using frequently for our trig ratio stuff, then you can think of that arc length on that unit circle being the radian measure of the angle. We learned our 6 trig ratio definitions, and I'm not going to go back through them all because you know them at this point. That vertical one right there is the what? That's the sine of the angle. So you know that's the sine of your angle, or it's the sine of that arc length in radian measure. And you also can notice if this angle is relatively small, like this picture right here, notice that that arc length is going to be pretty close in value to the sine reading. Okay? And so oftentimes in calculus, you're going to see that you're going to make an approximation. If you're dealing with small angle measure, you're going to say, boy, I can simplify the math by replacing the sine of the angle with just the arc length there. And then it makes it linear, because something just called t is going to be a lot easier than dealing with the sine of an angle. Okay. Now, back to the trig ratios. We have 5 numbers to memorize that I think you all have in your head already. And I'm going to just show them on the scaling over on this side so I don't mess that picture up. if we're at these type of angles shown with their terminal sides here, these are part of our 16 angles, then you know that there are heights here, there are x and y values on this circle, including 0 here, and these numbers are precisely 1/2, square root of 2 over 2, square root of 3 over 2, and 1 when you finally get up there. 5 simple numbers to memorize. And similarly, the x readings here are those same 5 numbers with the negative signs. -1 here, negative square root of 3 over 2 there, negative square root of 2 over 2 here, and negative 1/2 there. And that's what we use to come up with our trig ratios, as we've done repeatedly. Okay. Let's see if there was anything else in that section I wanted to mention. One quick example of that might be, let's say we wanted to do the secant of, let's say, 7 pi over 6. We would image where 7 pi over 6 happens to be as an angle, but we oftentimes are not going to be playing, we prefer not to be playing with the secant. We prefer to be thinking of what instead?
1 over the cosine.
The cosine, right? So 1 over the cosine of this, and we may not even prefer to be thinking of this in radians. Well, that angle is sitting right here. 7 pi over 6, no it isn't. Hold it. Now, how did I catch my mistake so quickly? What thinking did I, when I wrote this down here and drew it here, and I looked at that, why did I know right away, and you folks started laughing, why did I know right away that this is not right, placing it here? This is just a little bigger than 1 here, pi, isn't it? It's just a little larger than pi, isn't it? So I knew it should be over here. What I meant to say was, what? 11 pi over 6. Okay? That's the one I meant to write down. And that's almost 12 pi over 6, which would be 2 pi. So this is essentially like negative 30 degrees right there, isn't it? Or if you whip all the way around, 330 degrees. So if you prefer not to be using radian measure, feel free to kick it over into degree measure in an application like this. And then you come back and you're going to mentally image this. You're going to be visualizing this triangle like this. That's what you want to draw on your unit circle, and your theta can be thought of as the whole thing, or the negative 30 there being 330 degrees. And then you've got your 5 numbers to play with mentally. And at 30 degrees, this is negative 1/2, and this leg right here is square root of 3 over 2. So that means this cosine reading is the x leg. The cosine of that angle is the x reading over the radius, and the radius is 1, so that x reading there is square root of 3 over 2. And we drop that in right there, so we're dealing with the reciprocal of the square root of 3 over 2, which becomes 2 over the square root of 3. But we don't leave it that way. We multiply numerator and denominator by the radical 3 to rationalize the denominator, and write it like this. So there's the answer for your secant of that value.
Except it would actually be negative. Secant of 7 pi over 6 is actually negative.
Oh, I'm sorry. I didn't change the original problem. Come back here. Thank you. Okay, right? I changed that from a 7 pi over 6 because I'd drawn it over here, and I wanted it to stay there. So this needs to be an 11. Thank you for catching that. Okay, this matches this angle. Then we use our cosine, our understanding of cosine to develop that. Everybody good with that? Okay, let's see. That's probably adequate on that material. So again, that would be the first recording or the first session recording, and then this one would be the third recording. And then let's go ahead, and we've got time on this segment to go ahead and start on the properties of trig functions, and then we'll probably cut it off there, and then we'll start the second segment when we get to here. All right? Is this worth your time, going back on these things for people? Okay. If you're really good with this review probably isn't necessary, but if you have some shaky spots, it might be, I hope, is worthwhile. So let's look at the properties now. And once again, I want to mention the reason we're recording this summary is because I want you to be able, or you and other students, to be able to go back, and when you're in calculus, because you get rusty on these things, be able to go back and look at some of these things if you get shaky on it. Okay. In the way that this textbook has it laid out is they give you all these properties, but the way I prefer to present this material is to get you to the point of understanding the graphs. And then from the graphs, you can see the properties from the pictures. The issues that are coming up in this section of the book is domain and range, or our domain and range, and then also things such as the periodic type of character of the trig functions. And a quick summary of that, without me even drawing the pictures, which we'll get to in a moment, is the sine, the cosine, and their reciprocals, the secant, let's just do it in the traditional order, and so you got your reciprocal of your cosine here, and your reciprocal of your sine is going to be your cosecant. Those things, because of your understanding of the sine and cosine having periods of 2 pi, these reciprocal functions have that same period. So all 4 of these functions, 4 of your 6 trig functions, have a fundamental period of 2 pi. That means if you're calling these some f of theta, then f of theta is going to be the same as f of theta plus 2 pi. Or multiples of 2 pi added to theta. So you could put 2k pi in right there if you chose to. Is that right? Okay. The other 2 trig, oh, and then, hold it, that's the periodic stuff, sorry. Okay. That's the periodic issue. The domain and range issue here is a little bit different. So my bracket here isn't quite correct for what I just addressed. So let me stick with that for a second. Let me hold off for a second on domain and range. So the periodic character of those 4 functions is, because of the fundamental period of them, is going to be this kind of functional behavior. If you had the other 2 trig functions, if you had your tangent or your reciprocal of it, the cotangent functions, then their fundamental period is pi. So the function relationship there would be f of theta could be f of theta plus or minus pi, multiples of pi added to theta. Any questions on that? Okay, back to domain and range now. One way I've mentioned previously, and usually present it to help you understand this, is to draw the graphs. Another way we could think of it, though, is we could be thinking of our unit circle. And we know that on our unit circle, the sine readings again, are the y values, and the x readings here are the cosine values of your standard angle. You can see that there is no problem for sine for any angle choice. You can go plus angles, minus angles, as big or as small as you want, many times around, and so there's no problem in this domain issue here. So the domain on your sine function is all real numbers, or minus infinity to infinity. The range, however, is restricted to your y readings you see here, and they can't get any larger than 1 or any smaller than -1. So your range is trapped between -1 and 1. All right? Same thing will happen on cosine, because cosine can vary from as large a value as +1 over here to -1 over here. But there's no problem in the choice of the angles on the cosine. So your sine and cosine functions have that kind of behavior for domain and range. It starts to get a little more exciting when you go to the other 4 functions on domain and range. And so what you can think of, if you're then on to, say, the tangent function, you can be thinking of it as the y over the x, by definition, which is sine over cosine. And I think you can see that the range of values here for the tangent being sine over cosine, again, that reminds us of slope of the terminal side here, the slope of your terminal side. And you know those kind of values from your basic algebra background. They can vary from -infinity through 0 to positive values rising towards positive infinity. So the range of values on tangent is going to be all real numbers. The domain does have some restrictions. The domain does have some restrictions. And that's going to occur here when you have trouble with what? Stay awake. I'm talking so much that it's probably going to put you to sleep. But what's going to cause trouble for the domain of the tangent? Yeah, if that cosine heads towards 0 in value, you're going to have some trouble, because we can't have division by 0. And you know where that occurs by, again, thinking back to unit circle. That's going to occur if you're up here at 90 degrees or down there coterminal with 270 degrees. Okay? So it's going to include, so you can't write the domain down real simply. What you could do is you could say the domain is the set of all theta such that theta is not equal to, you have to get on one of the spots where you have trouble, like pi over 2. And then once you're on pi over 2, then they're going to occur, the trouble spot's going to occur periodically. How often?
2 pi.
Every pi on tangent. Remember, go back to the tangent or cotangent functions here. They're periodic on pi. Undefined tangent at pi over 2, you add pi to that or subtract pi from that, you're going to end up here with an undefined tangent as well. So the way you typically write that is you put an integer multiplier there times pi. So that's set notation describing that. Okay, now I didn't quite finish all the other functions, but go back and look at recordings number 4 and 5 if you need to address those issues. Okay, we'll go ahead and end this segment now, and then we'll continue on in a minute.